Assalamu alaikum everyone. My name is Shazia. I'm a year 1 medical student and I'm going to present 3.5 of biochemistry to you. So before we begin, I need to make sure you guys understand what acidity and dissolution mean. Acidity in technical terms is the tendency of a molecule, acid or base, to dissociate from its proton. That is, the more acidic a molecule is, the more likely it is to dissociate from its proton, and the less likely it is to take a proton back. Okay, so I'd like to think of it, and it's more efficient to think of it as acid meaning sour, right? So the bond between the molecule and its proton is a sour one. So when you have a sour relationship with someone, you're gonna stay away from them. You're gonna leave them quickly, and you're not so easy to get back with them, as compared to a less acidic, less sour, also known as more basic. In those bonds, the proton is more attached, so it's gonna have a harder time leaving the molecule and an easier time attaching back to the molecule. So you're gonna have an easy time understanding buffers if you think of it this way. Okay? Next up, we have dissolution. Dissolution is, simply put, when you add something to water or any solvent. When it dissolves, what happens? Water surrounds its individual ions or portions more easily than they attract each other. So usually solvation spheres surround the charges and leads to dissolution. Okay? Moving on. So I will give you guys time, a few seconds, to answer every question, or you can pause actually. So the answer is gonna be C, partial ionization of hydrogen atoms. So like we discussed, a stronger acid would more easily dissociate from its proton, right? So in case of a strong acid like HCl, you would have complete ionization, correct? You are completely dissociating H plus and Cl minus ions, so they have a more acidic or sour bond. Meanwhile, C, partial ionization, is what happens in case of weak acids. Okay, another question. What do you expect to find more in an acidic solution? The answer is going to be H3O plus ions, also known as hydronium ions. In theory, we follow B, H plus ions, because it is easier for when you look at an equation, it's easier to look at it as H plus than H3O plus. It's just that in practicality, H3O plus is formed by simply the attachment of the proton to a water molecule. That is all it is. So we just stick to H plus, okay? So here we have the dissociation of So here we have the dissociation of a weak acid, that is acetic acid, into its individual ions. So you have CH3COO minus, which is called the acetate ion, and its acidic counterpart, or the proton, since it has bound to H2O, it has formed the hydronium ion. It's only in this case that we look at it as H3O plus, but anyway. So weak acids undergo dissociation to a lesser extent, and they form a conjugate base. So when an acid from its neutrally charged state loses its proton, which is what acids do, right? It forms a negatively charged ion, and when an acid loses the positive charge and becomes this negatively charged ion, it is called a conjugate base. So acetate is the conjugate base of acetic acid, right? Next up, we have ionic substances like HCl and NaOH. What are they? Strong acid and strong base. So the strong acid completely ionizes into H plus and Cl minus, whereas NaOH completely dissolves into Na plus and OH minus ions. H plus we call a proton, OH minus we call hydroxyl or hydroxide ions. Okay, so they completely dissociate, which is why we have a single direction arrow, unlike in the first case, which we'll come back to. So here Cl minus is what? The conjugate base of HCl. Going back to this, we have a two direction arrow here. So what does that imply? Basically, we spoke that CH3COOH, acetic acid, is a weak acid, right? So it ionizes, let's go to this picture, but not completely. As you can see here, these kinds of molecules with the red and blue are the whole molecule of acetic acid, whereas this one here is the ion of acetate, and this is a proton. So when you add acetic acid to water, the extent to which they dissociate, hold on, can be understood like this. So the ones in purple ticks are the number of undissociated molecules of acetic acid, whereas how many can you see that are like the acetate ion, individual blue spheres? 3, right? And similarly 3 protons. So for a given number of acetic acid molecules, only a fraction of them dissolve into their ions, and that's why we call them weak acids. Okay, so this is the tendency or the nature of the substance, that only this much would dissociate in a certain amount of water or at certain pH. So what about in case of a strong acid, right? So what's gonna happen? It completely dissociates. So all you're gonna have are similar to H plus, and if these were Cl minus ions, you'd only find these two. You would not find the undissociated molecule in the solution in case of a strong acid. Okay? Moving on. So we have ionization of water. So say like HCl dissolves and forms H plus and Cl minus. Of course, the water can also form H plus and OH minus, right? So why don't we usually talk about this, or what is the significance of this, right? So this does occur in water, but it's to such a small extent that it's almost insignificant, okay? So I don't think this part is very important for your exams, but we'll just skim over it. So you have this equilibrium reaction, and it leads to the formation of an equation. We have an equilibrium constant, which basically tells you, going back to this slide, right? This is equilibrium, right? So you have X number of acetic acid molecules, and Y number of acetate and Y number of hydronium ions. So once they have reached the state of equilibrium, what does that mean? You will find constant amounts of acetic acid and constant amounts of these two individually. But it does not mean that every undissociated acetic acid molecule stays as it is undissociated throughout. No. As many acetic acid molecules dissociate into acetate ions, the same number of these individual ions associate back into acetic acid. Okay? So what are we saying? This brings us to the definition of equilibrium, that is, the rate of the forward and backward reactions are the same. So association this way and dissociation this way do occur, but it's not in unbalanced amounts. They occur at the same rate, so that the left-hand side and the right-hand side stay in the same concentrations. By same, I mean constant concentrations, not the same amount as each other. I hope that's clear. So back to this. So at equilibrium, right, over here, we have the product of the concentrations of the ions that are formed divided by the concentration of water in a beaker, for example, okay? So it gives you the idea of how much ions you find per molecule or concentration of water in the overall beaker. Okay, that is the idea of an equilibrium constant. Basically, how much of the reaction has proceeded, and how much is remaining in its reactant form. Okay, and for your information, that is such a small value. Okay, if you look at the equation, the graph on the left. Okay, say Z is the concentration of water. So it's something like this. It'll actually be somewhere on this level, whereas H plus and OH minus ions will not be here, but rather somewhere very small concentrations. Okay, so we have the equilibrium constant, and we use this value in other chemical topics, but not so much over here. Since H2O is in such a massive concentration, we would rather multiply it with the equilibrium constant and give us this equation. So the equilibrium constant multiplied by the water, right? The water product, ion product of water, is what we call Kw, okay? And what does this mean? It's literally just the product of the concentrations of the ions. So they are telling you how much ions you find in that beaker, and that comes to the value of 1 into 10 raised to minus 14. Okay, so that's a really small value, far less than 1. Okay, so if this is the value when you multiply it with how much water there is, imagine how much lesser the value would be if you divided it by the concentration of water over here. Okay, so that's why we have the ion product of water, since for two reasons. The concentration of water is so large that its ionization barely changes its value, so it stays somewhat constant, so we're multiplying it with the equilibrium constant. And the other reason is that it is a really large value. Okay, this part, however, is important to remember. For the ion product of water, the value is this, 1 into 10 raised to minus 14, and these are the standard conditions at which you find this value. So if you change the temperature, or say you change the pressure, the value would change. Okay? So these 3 points are important over here. Moving on. We have acids, bases, and pH. So what is pH? What is pKa? They basically give you an idea of acidity. Alright? So pH, what do we know about pH? The lower the pH is, the more acidic something is. How do we know how acidic something is? When you dissolve it in water, and the more protons that are formed, the more acidic it is. Yeah? So what is this? It stands for the concentration of protons or hydrogen ions, right? So lower pH, greater concentration of H plus. So between these two, the blue and the yellow, which one do we think has a greater value just by these numbers? 1 into 10 raised to minus 2 versus 1 into 10 raised to minus 4. It is going to be the one in yellow. So yellow is a greater concentration of protons, yeah? So when you have greater concentration of protons, it means you have more acidity, meaning you have less pH, or rather value of pH, right? I hope that is clear. Because when you put it into perspective, 1 into 10 raised to minus 2 means 0.01 moles of proton per liter of water. This is pH 2, that is like very low pH, okay? So pH 4 in contrast would be higher pH, meaning lesser acidity, meaning lesser proton concentration. Alright? The pH of water is 7. What does that mean? So it leads us to concluding that it's 1 mole of protons per, that's about, I think, 1 billion liters of water. So 1 mole of protons, by the way, it's not very important to know, but to put it into perspective, 1 mole of protons is about 1 gram of hydrogen ions per billion liters of water. So that's the amount of ions you find in water because it is neutral, so it doesn't have much, and it's this number. Anyway, numbers are not important. I just wanted to give you guys an idea of it, okay? Then we have pKa. By the way, this equation might need to be remembered. Minus log of H plus, which is why when you see minus log, the values are going to be inverse. The concentration, the higher it is, the lower the pH would be. Okay? Then we have pKa being minus log Ka. So it's a similar thing, but what is Ka? It is the dissociation constant for acid. And for your reference, this is only to give you an idea. This is not in your textbook. By no means do you have to remember it. Okay? So what does it say? It just gives you an idea of how much an acid dissociates into its ions in a solution, right? So how much ions you find per concentration of acid that you dissolve. It's similar to the equilibrium constant. Basically gives you an idea of how much ionization has occurred, right? But you don't need to know the equation. Moving on, we have amphoteric versus amphipathic. We have already discussed what amphipathic molecules are, which are molecules that contain both polar and non-polar regions or parts of the molecule. So in other words, hydrophilic and hydrophobic regions are found on the same molecule. That is what an amphipathic molecule is. So P for polar, non-polar, you can remember it like that. What is amphoteric? Basically molecules that have both acidic and basic regions or parts in their molecule, okay? That's about all you need to know at that point. Then you have pH versus pKa. So both of them give you an idea of the acidity of something, right? So what is that going to be? What's the difference? So these are two statements I took straight out of the textbook. One says at constant temperature, the pKa value of a substance is a constant. Second point says pH values of a system may vary. And pH versus pKa, basically, if you compare their equations, you're just going to end up with the difference between H plus concentration and Ka. So what is that difference? H plus concentration can vary for a system or rather a solution, right? So it doesn't matter what all you've added to it. The amount of protons you find in it is what your ultimate determinant is, okay? Meanwhile, Ka, we said it is the dissociation constant for an acid. At a constant temperature, the pKa value is constant. That means it only depends on the nature of the substance and nothing else except factors like temperature. Okay? So there's that. What is Ka? How much that substance dissociates into its ions. What is H plus? How much ions you find in, how much protons you find in a solution. Okay? By ions we mean H plus because we're talking about acidic dissociation constant. I hope that's clear. pKa has to do with the substance. H plus has to do pH has to do with the solution or system. Now I want you guys to guess what these labels could be. So the first one, it talks about HCO3 minus, H3PO4, and the column on the left says bicarbonate and phosphoric acid. So what is it? Yes, they are the names or chemical formula of the acids. Okay? Then we have CO2 minus and H2PO4 minus. With respect to the chemical formula, what is changing? You're losing an H plus. By the way, this is CO3 2 minus. Okay? Anyway, so HCO3 minus without a proton forms its conjugate base, which is CO3 2 minus, and H3PO4 without a proton would be H2PO4 minus. So that takes us to the conjugate base of this substance. That is its chemical formula here. Then, the third column, 5.6, we can ignore those values. What you have to focus on is this region, right? The 10 raised to something. So, what does this remind you of? pH or pKa? Yes, it's going to be pKa because we're talking about substances here. So when you see numbers like this, it's going to be with regard to pH or pKa, depending on whether you're talking about a solution or the substance. So which one of these two do you think is more acidic? 10 raised to minus 11. All you need to do to determine the pH, if you do not already know, is look at what is in the power. 10 raised to minus 11. So if it's minus 11, pH becomes somewhere around 11. If it's minus 3, it becomes somewhere around 3. Okay? These bits play very insignificant roles, like very trivial roles in determining the pH, as you can see. 10.33 is just a little lesser than 11, and 2.14 is just a little lesser than 3. So, the pH of this phosphoric acid is going to be around 3, and the pH of this is going to be about 11. So which one is more acidic? Phosphoric acid is more acidic. Bicarbonate is pretty much basic, actually. It's far more than 7, yeah? Now, the last column, what could it be? 10.33 is greater than 2.14, but 11, sorry, not 11, this value, something into 10 raised to minus 11, is a much smaller value as compared to something into 10 raised to minus 3, right? Which is a larger value. So as compared to this, 10.33 is larger than 2.14. So these are inversely proportional, yeah? So what could this be? pKa, right? Minus log of Ka. Khalas? You guys don't need to remember any numbers in this table. It is just for your reference and for comparison and to get an idea of what all these variables could mean. Then, question. The answer will be phospholipid, right? Amphipathic, we said it has hydrophobic and hydrophilic regions, which you can remember by polar or non-polar. So it's a phospholipid because why? It has a phosphate head and a non-polar or hydrophobic lipid region. A lipid is a massive long tail of hydrophobic carbon chains, okay? Now you might be wondering why we don't consider D, peripheral proteins, as an answer. That's because we know, yes, there are hydrophobic and hydrophilic amino acids, but the backbone of a protein, the most basic component of every amino acid, is what? The carboxylate, the acidic group, and amino, basic group, right? So they're gonna have a charge all the time, most of the time in the body at least, okay? Since they have charge, that makes them what? Hydrophilic. So for the most part of any and every protein, it's going to be polar, that is hydrophilic, and not in most cases not hydrophobic. That's why we say it's a phospholipid and not proteins. I hope that's clear. Okay, next up we have blood pH. Blood is one of the most important fluids in your body that need a constant pH, right? So what is that range of pH going to be? 7.35 to 7.45. And acidosis and alkalosis are the resulting diseases when the pH goes below or above the normal range. Okay, so firstly we're going to discuss what these conditions are, how they're caused, what the symptoms are, and then we're going to talk about how they are buffered, how the pH is buffered so we can maintain this range. So first off, you have acidosis, which is more acid in your blood, right? It is associated with tissue. So everything that's causing acidosis is happening in your tissues. There's an increased loss of base, decreased loss of acid, and increased production of acid, which has to do with metabolism. most of your metabolic byproducts, if not all, have protons that are increasing the pH of your blood. So we are constantly going to have to maintain that, right? So abnormally increased production of acid is one of these causes for acidosis. So all of these are occurring in where? The tissues, okay? Then we have diabetes mellitus, which is basically high blood sugar. Yes, it is a disease that leads to or involves acidosis as one of its symptoms. Okay, it's called diabetic ketoacidosis. If it's not mentioned in your textbook, you don't need to remember it. But yes, acidosis is one of the symptoms observed in this disease. Keep in mind, acidosis and alkalosis are not diseases on their own. They are just homeostatic imbalances or conditions at best. And the symptoms of acidosis are depression, coma, and death. So a simple way to remember it would just be, as you know, you have the cell and you have the outside of the cell having relatively positive charge as compared to the inside. So what happens, this is the normal case, okay? So when you have acidosis, the outside is going to be even more positively charged due to the presence of what? Protons, yeah? So the inside is going to be even more negative, even more sad or depressed than usual. So that's a way to remember how acidosis works, or the symptoms it causes. So depression, we mean the depression of the central nervous system, not mental, psychological depression, okay? Then we have coma and death. All are related to inactivity, negative, slow, low. You can associate it like that. Then you have alkalosis. Alkalosis has more vowels than acidosis does, so you can think of it as oral related condition. So it has to do with things occurring through your mouth. That is consumption of alkaline drugs, excess consumption of those, and prolonged vomiting. Your vomit has what kind of taste? It's acidic, right? It's sour. So you're losing more acid from your body with excessive vomiting. So it leads to alkalosis in your blood, okay? So both of these are occurring through the mouth. So that's why alkalosis oral, okay? The symptoms in this case are related to, coming back to this, right? The outside of the cell is more positive. The inside of the cell is more negative. When you have alkalosis, you're going to have more hydroxyl ions in your blood, yeah? Or extracellular fluid. Anything outside of the cell is being affected. So there's going to be more negative charge. So the inside becomes relatively positive. Keep in mind, it still has charge, but it's relatively more positive. So you have positive, like excitement, spasm of your muscles, you have convulsions, and in severe cases, respiratory arrest. Okay? Then we have why or how buffers work. So what is the principle that buffers work on? It has a name. It's called Elshaeir's principle. It basically says when you have a reaction at equilibrium, if you add something to it, if you change the conditions like pressure or temperature, the reaction's equilibrium itself will move to a point to neutralize that stress or change. Okay, so say you have a graph and this is 100% progress of the reaction, okay? Like dissociation of a strong acid would end over here, say it's 100%, okay? Over here, when you have an equilibrium, it usually stops at any point on this line. So there can be equilibrium at say 75%, okay? So what does that mean? You have 75% products and you have 25% of reactant in your solution or mixture. But when you add something, say for example you add more product, what's going to happen? It's going to shift the point of its equilibrium to another point. Okay, so whatever product it's formed, a certain portion of those products will come back to the reactant form and stay that way because now you have added another factor to the reaction. Okay, Also, not important, you just need to remember the principle and the fact that the equilibrium changes to relieve any change or stress. An example of this would be the acetate buffer. It is also a mixture of a weak acid and a conjugate base. So a weak acid, as we know, is acetic acid. What is a conjugate base? It is the acetate ion, right? CH3COO minus. Then we cannot have ions existing as they are when you're making a solution. You don't just have a bottle of acetate. You have sodium acetate or something that it's combined with, right? So that's gonna be sodium. Okay. So since this is what's the nature of the bond between acetate and sodium? It's an ionic bond, right? So when you dissolve them in water, they're going to completely become individual CH3COO minus ions and individual sodium ions. So it's as good as what? You have the weak acid and you have its conjugate base. So sodium is just there, but we will keep it in mind for this purpose. So how do buffers work? You have the weak acid and you have the conjugate base portion, alright? So first case, you are adding, say, acid or proton to this mixture, okay? So imagine a beaker, you have a mixture of these two components and you're adding more acid or protons. Forget the acid part, like say you're adding HCl, but let's just, for convenience, pretend you're adding protons alone, okay? So what's gonna happen? You're gonna attempt to reduce the pH. So H plus combines with the conjugate base portion over here and form acetate. And the sodium also remains separate. So both of these products are neutral. So you had proton in the beginning, but now it has been neutralized, right? When it's in acid form, it's not going to affect the pH. When the acid dissociates is when the pH changes, okay? Then we have the case in which you add hydroxide ions or increase the pH. The OH combines with the proton from the weak acid. So when you're adding a basic component, it combines with the weak acid component and forms water. And the remaining part is the acetate ion, both of which are neutral, right? So you have neither OH minus nor H plus in your product. So that's how it's gonna happen. Now, say you have in this mixture, so you have more conjugate base than weak acid. So you have more of this. This conjugate base portion buffers out what? It buffers out H plus, right? H plus attempts to decrease the pH, but it buffers this out, so it's gonna maintain a higher pH, okay? Similarly, we're gonna have, say, I want you guys to think about this yourself and see if you get it right. So you have a higher weak acid component, it's gonna buffer out more OH minus ions. Sorry for that. It's gonna buffer out more OH minus ions, so it's reducing an increase in pH. It's preventing this from happening because you're buffering out this OH. So you're gonna maintain it at a lower pH. Easy to remember though. Acid meaning lower pH, base meaning higher pH, okay? Now what happens if you have them in equal amounts? So, we spoke about pKa and pH. We said pKa has to do with the nature of the substance while pH is of the solution. You don't need to remember why or how this happens because it has to do with a complex equation that you do not need to learn. But basically, the nature is the same as the solution itself. So the classic cliche dialogue, you know, I am at my best when I'm myself, when I'm being myself kind of thing. So its maximum buffering capacity occurs when its pH is the same as the pKa of the buffer. Alright? So from this we have two factors that affect the capacity of a buffer to buffer. And that's gonna be one, the concentration of the buffer itself, the two components of the buffer, and the ratio of their concentrations with regard to each other. Okay, so what is it? The quantities of both, one with respect to the overall solution, okay, and against each other. So if you have more of both weak acid and conjugate base, you're going to be able to buffer more molecules or more moles of acid or base. Clearly, it's just a quantity, right? And the ratio of their concentrations, so as we discussed in blue, the more acid, the lower the pH you can maintain, the more base, the higher the pH you can maintain. Okay, I want you guys to answer this. Hint, and that is, if you have more weak acid than conjugate base, you're gonna buffer more what? OH minus. So if you want to buffer out H plus, you're gonna need more conjugate base. Okay. Now the Henderson-Hasselbalch equation is not very important, neither do you need to remember it, but just in case you do need to, I like to remember this as, so there's a negative sign here, a negative emotion. Say you pronounce this out loud, you're gonna have ha, it's like you're sighing, it's a negative emotion, so you can remember it that way, while on the other hand this is aha, it's a positive emotion, so there's a plus sign. Alright? If you do need to understand what the equivalents are, you can just read through this, but I believe it's not that important and I don't want to waste any more of your time. So, at this point, you can see that the pH of the solution is equal to the pKa. So what is that? The pKa is the pH at which this compound ionizes. So the more OH minus you keep adding, at one point, which is this point, is where the maximum of this molecule will dissociate into this plus H plus. Okay, so that H plus is combining with OH minus and forming water. Okay, so this formation of water, because you are releasing proton to buffer with the OH, is what is causing this decrease in slope. Okay, so once, say, you're reaching this part, okay, you're adding more and more sodium hydroxide, after one point you're running out of the acetic acid molecule, and most of them are in this state, right? So what's gonna happen? You're gonna run out of dissociating molecules of protons to buffer out the OH minus. So at this point, the more OH you add, just as much the pH will increase. There's gonna be no more buffering at one point. Okay, so that's why you can see this increase here, and similarly the other way around, downwards. Okay, I hope that is clear. So when you have a more weak acid component than conjugate base, the buffer is gonna be somewhere around here in this region of the box. If you have more conjugate base than weak acid, it's gonna be buffering around this range. So if you add on this side more acid, it's gonna be more prone to getting out of its buffer range and falling into more acidic state. And similarly for base, but anyway. So if you have an equal composition, the concentrations are at the same ratio, same concentrations of each other, it's going to be happening at this range. So as much acid as you add, as much base as you add, it's going to buffer equally efficiently. Okay? The x-axis is also called the abscissa, if you need to know. Before we talk about this, let's go to amino acids. So far we've discussed protons dissociating from their molecule in cases of acids. You can have more than one proton, more than one hydrogen ion on a molecule in so many cases, okay? So one of those examples is amino acids. Amino acids have ionizable protons, or ionizable hydrogen atoms on this side. This is what the carboxylate or acid group, right? And this is the amino group, and it already has a proton. So these two are the ones that can dissociate from the molecule at different pH. Alright, so between this proton and this proton, which one do you think will leave more easily or is more acidic? Obviously, it's going to be the one belonging to the acidic group, yeah? So the carboxylate group has a more acidic proton, we say, and amino group is more basic. So the H plus has a greater attachment to the amino group. So at a low at a low pH, when you don't have much of base, right? It's a very acidic state, say 2.3, right? It's a very acidic state, so you don't have much hydroxide ions, so they're all in protonated state. Now you need to know, for acid, right, it does what? It gives away protons. So from its neutrally charged state, it's gonna become negatively charged, form its conjugate base. On the other hand, when you have over here to the right, the amino group, when it's neutrally charged, it abstracts protons, right? It's a base, so it takes protons and receives a positive charge, so it becomes a conjugate acid, okay? So that you need to remember, because this is called a Zwitter ion. Basically, both are doing their task. The base has abstracted a proton and the acid has lost a proton. So they have one negative and one positive charge, but as a whole, the molecule is neutral. So this is what a Zwitter ion is called. Zwitter ion is. Now, back to this. You have low pH. You have acid and base groups being protonated, right? Now, at a very low pH, you don't have that many hydroxide ions, but you add more hydroxide as you go, so you're increasing the pH along this direction, okay? So you're gonna add more and more base until at one point, this proton is gonna start to dissociate from each of the molecules one by one, right? And that is the pK1, okay? The first group to deprotonate, right, dissociate its proton, is going to be the most acidic group because it requires minimum hydroxide ions to dissociate and buffer it out, okay? In the second pH, or pK2 as we can call it, before that point we have all of the acid groups becoming carboxylate. That is, they are now in their conjugate base form, okay? Now in pK2, you're gonna act on NH3+. Since it's protonated, you're still adding more hydroxide ions. So at one point, that is 9.7 pH, the protons are going to be removed from every amino acid's amino group, okay? And they're gonna buffer out, and that's why we have another point of equilibrium over here, okay? So what's happening? Basically, higher pH is needed to remove the more attached proton because it's a more basic group, alright? So it dissociates, it buffers with the OH minus that we are adding in the forward direction if you're increasing pH, and it's gonna form water molecules for a bit during this equilibrium phase. And once all the amino groups have lost their protons, they're gonna go past this equilibrium point and the pH is gonna increase again, yeah? Now, at the highest pH, after pK2, you're gonna have both of them in their deprotonated forms. Alright, I hope that is clear. In the reverse direction, what's gonna happen? You're just gonna be protonating. So acid, more sour bond with its proton, so it's gonna take it back as late as it can. Meanwhile, the amino group is less acidic, so it has a stronger attachment to its proton. So when you add protons at this pH, the amino group will accept it more easily than the carboxylate group. Carboxylate deprotonates first more easily, but it gets protonated last, okay? it will all make sense if you just think about it as sour, acidic, more tendency to leave the proton alone. More basic, less acidic, more attachment to the proton, so the more easily it will be added back and the less easily it will be removed. Okay? You'll be going through this a lot more in detail in the proteins chapter, so I will leave this as it is. Alright? Now, coming back to phosphoric acid or other polyprotic acids, that is, unlike amino acids, right? They where the protons are found on both an acidic group and a basic group. Here you have protons being found on all three sides of a PO4 group. So basically they are symmetrical. There is no telling which one is more acidic or basic based on their structure or where they are found. Alright? So you have three ionizable groups that are the three H pluses, and each one has a pH at which the slope reduces. So the first pH would be the most acidic proton that gets released, right? Except here it's not that logical since all the protons are equally acidic, right? So it's just a matter of which one goes first and which one goes last. Anyway, so I think it's pretty self-explanatory after the amino acids part. Okay, so in your pK1, the H3PO4, H2PO4 combination occurs, and in pK2 you have H2PO4 and HPO4 minus, and similarly for the third case. So the first one to leave is the most acidic, first one to come back is the least acidic and most basic, and so on. Now what's causing the decrease in slope? It is the buffering of H plus or OH minus depending on the direction. So in this direction it's addition of OH minus. So the OH minus is being buffered by release of the first proton. Okay? Which leads to the formation of water, right? And this water is what's causing the decrease in slope, since there is neither H plus nor OH minus in the solution at that point. Okay? Now we have three types of physiological buffers, the first one being the most important because it plays the biggest role in your blood. So this buffer is called a bicarbonate buffer, because over here you can see H2CO3 is your acid, weak acid. Okay? Now, how firstly is this weak acid formed in your body? Your body is 97% water, so the more carbon dioxide you breathe in, the more of it gets combined with water and converts to carbonic acid, that is H2CO3, right? Now, one carbonic anhydrase is the enzyme that allows this to happen at very, very fast rates. Otherwise, we would have just CO2 and H2O around in the body, and that is not good. Okay? Now, H2CO3, secondly, does not have a high concentration in your body. It's like a seesaw. Okay, you have a seesaw here, the center, and you have this. So H2CO3 is like this one guy in the center. It's not present in a high concentration. It either tips to the CO2 and H2O side, or it's going to tip to the conjugate base and proton side. It's not going to stay at a high concentration itself, right? So what's going to happen? It's going to form either these reactants or these products. Okay, now the pK1, that is the equilibrium between H2CO3 and HCO3 minus, right? This is the acid conjugate base pair, right? Weak acid conjugate base. The pH at which this equilibrium occurs is called a pK1, which is 6.3 of pH. So that is relatively lower than our blood pH, right? So what are we gonna do? We're gonna have much more conjugate base, that is our bicarbonate in the blood, than we have of carbonic acid or CO2, because this guy is relatively insignificant. We're just going to compare between CO2 and H2O, or HCO3 and H+. But we remember carbonic acid because that is our weak acid component. Okay, so now if you have this side in higher concentration for whatever reason, you're gonna have to get rid of those in a certain way, and that is by your kidney. Okay, the H plus and HCO3 minus are both excreted or retained by the kidney. Alright. On the other hand, this side, water, we know it is excreted or retained in multiple ways. Our main concern is carbon dioxide, and we know how it's adjusted by respiration. Simple. Okay. So when you have 20 times more bicarbonate than carbonic acid in your body, what does that mean? You're gonna have the buffer range, and it's gonna maintain its pH at this really high range, because what is this region? It's gonna be something like 6.3, because that's its pK1. So when you have equal amounts of the acid and the conjugate base, this is gonna be the range or region of the buffer. But when you have more base than acid, right, more bicarbonate ions, they're gonna buffer at this higher range. So you maintain it around 7.4 in this way. Okay? I hope that is clear. Question. In chronic obstructive pulmonary disease, patients are unable to pass carbon dioxide from the blood into air. Under these conditions, the patient would be in which state? Okay, so here I want to point out one thing. Firstly, you need to frame the answer in your mind. See if it's available in the options, okay? And then start reading each of the options and take a look at what is factually correct or incorrect. Now, for example, alkalosis above 7.5, it's correct factually. Acidosis below 7.35, correct factually. Alkalosis below 7.35 is wrong. We do not have below 7.35 as alkalosis, it's acidosis. And similarly, acidosis is not pH above 7.45. So we have 3 different options left, all of which could be possible. So now we're going to break it down. Let's see. So here we're not talking about what alkalosis or acidosis is causing in the disease, but rather what the disease is leading to, whether it's alkalosis, acidosis, or death. Okay, that's the first thing I want you guys to keep in mind when you read this question. So what is the result of not being able to pass carbon dioxide from the blood plasma? So when you have high carbon dioxide, what's it gonna do? Combine with water, form carbonic acid, yeah? And when there's too much carbonic acid, it's obviously, so you're retaining more and more carbon dioxide as time progresses, which will be pushed into more and more H2CO3. So obviously, for equilibrium purposes, it's going to lead to the formation of bicarbonate and H+, right? So there's more and more protons in the body. That's all it is. So it leads to alkalosis, right? Obviously, we're going to ignore this option of death because it's not that severe of a case, and we are talking about how buffering would react to this, okay? So this really confused me back when I was doing this chapter, so I wanted to make sure you guys understood this, so I really hope it's clear. Moving on. The next buffer is phosphate buffer, and it's at pK2 because the original phosphoric acid is H3PO4. So pK1 would be H3PO4 and H2PO4 minus. Now this is pK2, at which its combination is of weak acid being H2PO4 minus and the conjugate base being HPO4 2 minus. Okay? So this pH of pK2 is 7.2, sorry. So it's much more ideal for the blood than bicarbonate, you would think, right? Of course, it's true, but there's a problem. You do not have as much phosphates in the blood as you do for bicarbonate. So bicarbonate's gonna play a larger role there, and what is phosphate gonna do? It's gonna play a larger role inside the cell. So outside you have the bicarbonate, inside you're gonna have the phosphate. Okay, so inside the cell also you need to maintain the pH, so that's what phosphate is gonna do. And since the pH is ideal, you're gonna have an equimolar mixture, right? pK equals pH. Now, you have other acids as well in the body. Phosphoric acid is not the only one. Lactic acid, among others, also exist, but they have a very low pH of around 3 or 4 and very low concentrations as compared to phosphate as well. So these are the major limiting factors that prevent other components or acids from acting as buffers. Last buffers, and yet the most physiologically important ones, other than bicarbonate because it's that important for your blood alone, altogether throughout your body, proteins are found everywhere, right? They're the building blocks, the structural units, everything. You find amino acids left and right everywhere in the proteins, and you have so many proteins in your body. Anyway, so that leads to us talking about them being significant, and they are found in high concentrations, right? There's so many amino acids in one single protein. It's more than 50 amino acids to be called a protein. You have so many of those proteins in so many different varieties, so you have many ionizable groups. So imagine how much they can buffer, okay? There's that. Then you have examples: hemoglobin found inside the red blood cells, and serum albumins found in the serum, also known as plasma, okay? They contribute to buffering for two reasons: their structures and concentrations. Thank you.